According to Zaitsev rule, which will be the major product? Of course, this will be the major product because two alkyl groups you are getting here. Here only one alkyl group you are getting. Diazonium part will be substituted by the halogen, and N2 you can see that will be removed as nitrogen gas. In chlorine, there will be three lone pairs, right? One electron is forming a bond here and the other three will be lone pair. Now this one lone pair will be shifted here, and what happens? The double bond will be formed here. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry. So today we are back with session 5 of the chapter Haloalkanes and Haloarenes. So in the last session we discussed about the SN1 and SN2 reactions and the mechanisms in detail, right? As well as the stereochemical aspects of SN1 and SN2 reaction, right? And also the order of reactivity of various alkyl halides in SN1 and SN2. What is the order of reactivity of alkyl halides in SN1 as well as SN2, whether it is tertiary, secondary, primary or primary, secondary, tertiary, all of that were discussed in last session. So in today's session, we are going to move on with the next set of reaction, that is, as of now, we have completely studied about the nucleophilic substitution reactions which is happening in haloalkanes. So the next type of reaction we are going to study is elimination reactions. After that, we will be studying about reaction with metals. Then we are going to move on with the reactions of haloarenes. Okay, so till now we were discussing about haloalkanes, right? So once we are done with these two reactions, we'll start with haloarenes. Okay, so beginning with the first one, that is elimination reaction. So from the name itself, we can tell we are going to eliminate something. Before this, we have studied substitution reaction, that is, one is being removed, another one is being attached there. There is a replacement which is taking place. But in this case, we are going to eliminate something. That is, there won't be any substitution. We are going to eliminate it. Okay. So let's see. When a haloalkane with beta hydrogen atom. Now, what is beta hydrogen atom? I'll explain. Is heated with alcoholic solution of potassium hydroxide. That is KOH. There is elimination of hydrogen atom from beta carbon and a halogen atom from the alpha carbon. So what you have to remember, there will be elimination of hydrogen from the beta carbon and halogen from the alpha carbon. As a result, an alkene is formed. So what you are getting in elimination reaction? Alkenes will be the product which is formed. Since beta hydrogen is involved in the elimination, it is also called as beta elimination. So specifically, you can call it as beta elimination. So let's take an example and understand this. So let's write CH3, CH2, and you have an halogen. So in presence of alcoholic KOH, what did we just say? Beta elimination will take place. So what is alpha and what is beta carbon atom? So alpha carbon atom is the carbon atom to which the halogen atom is directly attached. So where is your halogen atom here? Halogen atom is present here, which is attached to this carbon. So this is your alpha carbon atom. So adjacent to that, the next carbon atom, the adjacent carbon atom is your beta carbon atom. So the hydrogen present in the beta carbon atom is called as beta hydrogen. So in here you can see this one is beta hydrogen, this is also beta hydrogen, this is also beta hydrogen, right? Whereas this is alpha carbon, so these are alpha hydrogens. Okay, so I hope alpha and beta is clear for you. So now what is happening here? As discussed, there will be an elimination of hydrogen atom from the beta carbon. So either of these three can be eliminated, as well as the halogen will be removed. So let us consider this hydrogen and this halogen is being removed. That is, hydrogen from the beta carbon and halogen from the alpha carbon is removed. So as you can see, if it is removed, means these two bonds are being removed. Okay, so when these two are removed, what will happen to the tetravalency of carbon? As you can see, then carbon will have only 1, 2, 3 bonds. This carbon will also have only 1, 2, 3 bonds. Is it possible? No, right? It should have 4 bonds. So if it is something is eliminated, what happens? A double bond will be formed there. So what happens? This is already eliminated. HX is eliminated. What happens? You have C here, you have one hydrogen here, you have another hydrogen here. Then you will get a double bond here and you have another hydrogen. That is CH2, double bond CH2. Now what is this? You got your alkene. So specifically you can say this is ethene, right? You obtained ethene. Okay. And what is being removed from here? H, and whichever halogen you have taken, that will be eliminated. So I hope it is clear. So in elimination reaction, as hydrogen and halogen is being removed, you will get an alkene. So this is what you have to remember. Beta hydrogen will be removed, and alpha, from the alpha position, halogen will be removed. Always hydrogen will be removed from the beta position. Okay. So if more than one beta hydrogen is present, as you can see, more than one beta hydrogen is present, there is possibility of formation of more than one alkene. Such reactions takes place according to CBSE rule. Okay. So if more than one beta carbon is there, more than one beta hydrogens will be there, right? In such cases, how do we decide which will be the product form? So let's take an example and understand. So first of all, we need to understand that in such cases, CBSE rule will be followed. According to CBSE rule, we will be determining which product will be formed. Okay. So first for that, we need to understand what is CBSE rule. In dehydrohalogenation reaction, so this elimination is also a dehydrohalogenation reaction. What does that mean? D stands for removal. We are eliminating, right? Hydrogen is removed. So for that you have hydro. Halogen is removed. So for that you have halogenation. So that is dehydrohalogenation. That means hydrogen and halogen. HX is being removed. Clear? So that is elimination reaction we are talking here. The preferred product is that alkene which has the greater number of alkyl groups attached to the doubly bonded carbon atoms. So if there is more than one beta carbon, that is more than one beta hydrogen possibility is there, then which alkene is having the more number of alkyl groups, that will be the preferred product. So let's take example and understand. You can see this is 1, 2, 3, 4, 5. So this is 2 bromo. On second carbon atom, you have a bromine group, right? So 2 bromo, 5 means it is pentane, right? Okay, so this is the haloalkane which is taken here in presence of alcoholic KOH. What did we discuss now? This will be your alpha carbon. Of course, the halogen is attached to this carbon, so that will be your alpha. So adjacent to this alpha carbon, now you are having 2 beta carbons. This is also beta carbon. This is also beta carbon, right? Both of them are beta. So, of course, these 2 hydrogen atoms are also beta hydrogen atoms. These 2 are also beta hydrogen atoms. So, either the hydrogen from here and this halogen can be removed, or else a hydrogen from here and this halogen can be removed. So, based on that, there are 2 possible products that you can get, which is mentioned here. So, in the first case, we are going to consider the hydrogen atom being removed from here and the halogen removed. Okay. So, in that case, what happened? The hydrogen is removed from here means a double bond will come between the third and the second carbon atom, which is shown here, right? So, you get pent-2-ene. On the second carbon atom, you will have the double bond between second and third carbon atom. Another possibility is hydrogen can be removed from this beta carbon atom. So, what happens? A double bond will be formed between first and second carbon atom, which is shown here. So, how do we decide which is the major product, which will be considered the major product? It will be based on the number of alkyl groups attached to the doubly bonded carbon atom. So, here this is the double bonded carbon-carbon atom, and here is the double bond which is present. So, to this double bond which is present, here is one methyl group, another ethyl group is also there, 2 alkyl groups. But here you can see you have one, this is the double bonded system, but you have only one alkyl group, which is propyl group. Okay. So, here you are having 2, here you are having 1. So, according to CBSE rule, which will be the major product? Of course, this will be the major product because 2 alkyl groups you are getting here, here only 1 alkyl group you are getting. So, based on that, you can decide if more than 1 beta hydrogen is present. So, this is about elimination reaction, that is beta elimination or dehydrohalogenation reaction. So, the CBSE rule is very, very important statement of that, as well as how to apply and identify which is the major product is important. Moving on to the next type of reaction, that is reaction with metals of haloalkanes. Okay. So, action of magnesium. First one, the metal we are using is magnesium, which is the formation of Grignard reagent. Okay. So, Grignard reagent is used for the preparation of various other organic compounds also. So it is very important how to prepare Grignard reagent. So one method, from haloalkane, by the addition of magnesium we can get Grignard reagent. So when an alkyl halide is treated with magnesium in presence of dry ether, alkyl magnesium halide is formed. So this alkyl magnesium halide itself is called as Grignard reagent. So as you can see here, alkyl halide is taken in presence of magnesium and dry ether, RMgX. This is called as alkyl magnesium halide. So for example, let's take CH3Cl in presence of magnesium, in presence of dry ether. What happens? You will get CH3MgCl. Okay, so this is one example of a Grignard reagent. Okay, so this is the first one, that is reaction with magnesium. Okay, moving on to the next one, that is Wurtz reaction. This is very important. Of course, as it is a name reaction, it is a very, very important reaction. Okay, so alkyl halides, when it is heated with metallic sodium in presence of dry ether, to give alkanes, it will give alkanes. So this was magnesium, now we are using sodium. Okay, so alkyl halides 2 moles we are taking, 2 moles of sodium in presence of again dry ether. What you are getting? Alkane you are going to get, and sodium halide. So what does that mean? Let's take an example here also, CH3Cl. Okay, chloromethane, 2 moles we are taking, right? So I am writing the 2 moles of sodium here. Again, 1 more mole of methyl chloride we require, right? So I am writing it is like this, ClCH3. This means the same, right? CH3Cl, ClCH3. It's the same, okay? So in presence of what? Dry ether. What happens here? What happens here? How you are getting the alkane is, this much part will be removed. That is 2Na and 2Cl will be removed as 2 NaCl will be formed. Other than that, you have what left? One CH3 here, another CH3 here. That is CH3, which is C2H6. What it is? It is ethane, right? Alkane is formed. Okay, so this is the way it will be formed. Now, another example, let us take C2H5Cl, 2 moles of sodium, and Cl, C2H5. Okay, so if we write in this format, it will be easy to understand. That is why I have written like this. In presence of dry ether, what happens? This much part will be removed. So you get C2H5. That is C4H10. What it is? Butane, right? So C2H5, which is butane. What is removed from there? 2 moles of sodium chloride. So I hope it is clear. So that is Wurtz reaction. Now we are going to study about haloarenes. First we will be studying about the preparation of haloarenes, then the chemical properties, that is various chemical reactions of haloarenes. Okay. So first, preparation of haloarene. So what is haloarene? In an aromatic group, the hydrogen is being replaced by a halogen atom, right? Okay. So first one is by electrophilic substitution reaction. So we have studied nucleophilic substitution reaction. So now here we are studying electrophilic substitution reaction. What is electrophilic substitution? We are going to substitute the halogen atom by an electrophile. Now what is electrophile? Electrophile, word itself means that it is having attraction towards electrons. So now what is electrophile? A species which is having attraction towards negatively charged substances. So that means it itself will be positively charged, right? Okay, let's understand. Aryl chlorides and bromides. Aryl chlorides and bromides. So what does aryl chloride means? On benzene ring you have a chlorine or bromine. Okay, aryl chloride and bromides can be easily prepared by electrophilic substitution reaction of arenes with chlorine and bromine respectively in the presence of Lewis acid catalyst like iron or iron chloride. Okay, so we have taken toluene here. What is toluene? A methyl benzene is called as toluene. That is, on benzene you have a methyl group to which we add X2. X2 stands for either it can be chlorine or bromine. That is your halogen. What happens in presence of iron? What happens? Yes, in the ortho position, your halogen can be substituted, or else in the para position, the halogen will be substituted. So what happens in this case? As you can see, this is the methyl group where it is attached. This is the ortho position. This is the ortho position. This is meta position. This is the para position, and this is also the meta position. Right? Okay. So the products that you are getting will be either in the ortho position or in the para position. Right? This is the ortho position and this is the para position. The ortho and para isomers can be easily separated. due to the large difference in their melting point. So ortho product and para product, both you are going to get here. So is it difficult to separate? No, it is easy to separate because their melting points will be differing more. So it's easily to separate them. Okay, so this is how haloarene will be formed according to electrophilic substitution reaction. Right, now moving on to the next method, that is Sandmeyer's reaction. So it is a very important reaction, Sandmeyer's reaction. So when a primary aromatic amine, we are using a primary aromatic amine. Okay, amine means NH2 group, right? So this is your primary aromatic amine, which is also called as aniline, right? It is aniline. Okay, on benzene you have NH2 group. Dissolved or suspended in cold aqueous mineral acid, it is treated with sodium nitrite, a diazonium salt is formed. So this is the first step, a diazonium salt will be formed. Mixing the solution of the freshly prepared diazonium salt with cuprous chloride or cuprous bromide results in the replacement of the diazonium group by chlorine or bromine. So let's understand this, that is the diazonium salt, how it is formed, and further how you are getting your haloarene. So for that, first you need your amine, which is a primary aromatic amine we are taking, which is aniline. So in presence of sodium nitrite and a mineral acid, it can be HCl or HBr, hydrogen chloride or hydrogen bromide we are going to take in 273 to 278 Kelvin in cold condition. What is going to happen? First you are going to get a diazonium salt, that is N2 plus X minus will be present. So for example, let's take, it's written benzene diazonium salt. Why diazo? That diazo means N2. Okay, diazo stands for N2. So let's take an example. We have taken aniline and sodium nitrite, and we are going to add HCl. If we are going to add HCl, what is the diazonium salt we are going to get? It is N2 plus and Cl minus. So according to which halogen you are going to take, you will get a benzene diazonium halide. Okay, now to this benzene diazonium halide which is formed, we are going to add the cuprous halide. It can be again chlorine or bromine in presence of this. So Cu2Cl2 or Cu2Br2 you can add. Accordingly, what happens? This diazonium part will be substituted by the halogen, and N2 you can see that will be removed as nitrogen gas. So nitrogen gas will be evolved. What is only left behind there? The halogen will be left behind. So taking the same example, what is happening? This is the benzene diazonium halide, and to that in presence of Cu2Cl2, let's take cuprous chloride. What happens? Nitrogen gas will be liberated and you will get chlorobenzene. So this is how haloarene is formed according to Sandmeyer's reaction. So this is an important reaction where you can get chlorobenzene or bromobenzene, right? Now the replacement of diazonium group by iodine does not require the presence of cuprous halide, and it is done simply by shaking the diazonium salt with potassium iodide. So here we have discussed, once we get the benzene diazonium halide, what we have to do, we have to add the cuprous halide. It can be cuprous chloride or cuprous bromide. According to that, you will get chlorobenzene or bromobenzene. So if you require iodobenzene, once the benzene diazonium halide is formed, you just have to shake it with the presence of potassium iodide. What will happen? The diazonium part will be substituted by iodine and nitrogen gas will be evolved. Okay, so I hope this is clear. In case of iodobenzene, how we can prepare it, I hope it is clear. Now we are going to study about the various reactions of haloarenes. So these three were the methods of preparation of haloarenes. Now we are going to the chemical reactions of haloarenes. First one, again we are going to study nucleophilic substitution reaction. So already we have studied this in haloalkanes itself. So aryl halides are extremely less reactive towards nucleophilic substitution reaction due to the following reasons. So we have studied SN1 and SN2 mechanism in detail while we were studying about haloalkanes. But coming on to haloarenes, they do not show much reaction towards SN1. But coming on to haloarenes, they do not show much reaction for substitution nucleophilic reactions. Now why is that? There are few reasons. The first one is resonance effect. Okay, so due to resonance, it won't be showing much preference to nucleophilic substitution reactions. So in haloarenes, carbon-chlorine bond acquires a partial double bond character due to the resonance. As a result, the bond cleavage in haloarene is difficult than haloalkane, and therefore they are less reactive towards nucleophilic substitution reaction. So what does that mean? due to resonance effect, this is going to take place. So as you can see, in chlorine, there will be 3 lone pairs, right? One electron is forming a bond here and the other 3 will be lone pair. Now this one lone pair will be shifted here, and what happens? The double bond will be formed here. So you will get a double bond here, which is shown here, the double bond. So as the electron is being shifted down and it forms a double bond, what happens here? The chlorine is losing its electron, so chlorine will get a positive charge. Okay. Now what happens? From here, the double bond has shifted and become a charge. Okay. Now the charge has shifted here and become a double bond. Now the charge here has shifted here and become a double bond here, and the double bond has shifted here and become a charge here. That is your first structure itself. So this is the resonance which is taking place. Various resonance structures I have shown here. So here what you can understand here, in all these 3 cases you can see the double bonds which is present. So as there is a double bond between this carbon and chlorine bond, the carbon chlorine bond has to break and then only the nucleophile can attach there, right? Because there is a double bond which is present here, it will be really difficult to break this bond and the nucleophile to attack here. So that is why, because of the resonance effect, as there is a double bond which is formed, it will be showing less reactivity towards nucleophilic substitution reactions. Okay. Now the another reason is difference in hybridization of carbon atom in carbon halogen bond. What does that mean? In haloarene, carbon halogen bond is less polar as carbon is sp2 hybridized. However, in haloalkane, the carbon is sp3 hybridized. As a result, carbon halogen bond is shorter in haloarene and it is difficult to break. Okay, so as you can see here, this is your haloarene. So in this case, you can see this is the carbon atom, okay, to which 1, 2, 3 and 3 further atoms are attached. One carbon atom here, one carbon atom here, another halogen atom. So this is sp2 hybridized, and in the case of haloalkane, what you can see, one carbon atom here, another atom here, another atom here, another atom here. So a total of 4 atoms. So this is sp3 hybridized. So the hybridization, if you compare in case of haloarene and haloalkane, this is sp2 hybridized, this is sp3 hybridized. Okay. So as the S character is more in the case of haloarene, the bond will be stronger. Okay. So in such cases, what will happen? As it is stronger, it will be shorter. This bond between the carbon and halogen will be shorter, and because of that, it will be difficult to break this bond. Okay. So that is another reason. First reason, as we discussed, was the resonance effect. Second reason is because the difference in hybridization. As it is sp2 hybridization in haloarene, it becomes difficult to break the bonds. Now, the next one is instability of phenyl cation. Phenyl cation is not resonance stabilized. Okay. So, what is phenyl cation? As you can see here, this is the haloarene, right? From this haloarene, if this halogen is being removed, what will happen? When the halogen is removed, a phenyl cation will be formed. So this is called as a phenyl cation. So now this phenyl cation will not be resonance stabilized, hence it is not showing resonance. So that will be another reason for the less attraction towards substitution nucleophilic reaction. Now the last one is high electron density on benzene. Because of the possible repulsion, it is less likely for the electron rich nucleophile to approach electron rich arenes. Now what does that mean? As we have seen in this resonance structure also, see in this ortho position you are having a negative charge, in this para position you are having a negative charge, in this ortho position also you are having a negative charge. So as you can see, this benzene ring or this haloarene is itself already electron rich, and it has to undergo nucleophilic substitution reaction, means another nucleophile is going to come which is also negatively charged. So this negative charge and the nucleophile's negative charge will be having a repulsion between each other, hence it will be more difficult to undergo substitution nucleophilic reaction. So as discussed, they will show less attraction towards substitution nucleophilic reactions, but still they will undergo these reactions. So first reaction we are going to study is the replacement by hydroxyl group. Okay. So under that, first one in chlorobenzene. So chlorobenzene can be converted into phenol by heating in aqueous sodium hydroxide solution at a temperature of 623 Kelvin and a pressure of 300 atm. Okay. So this is your chlorobenzene in presence of sodium hydroxide. So this temperature and pressure is important. What happens? The halogen will be replaced by the nucleophile. As we are using NaOH, what is a nucleophile here? OH, right? So phenol will be formed. On benzene ring, you have OH, that is called as what? Phenol. So this is In case of chlorobenzene, when it is reacted with sodium hydroxide in the given temperature and pressure, you get phenol. Next one is in chloronitrobenzene. Okay, chloronitrobenzene. So the presence of an electron withdrawing group at ortho and para position increases the reactivity of haloarenes towards nucleophilic reaction. However, no effect on reactivity of haloarenes is observed by the presence of electro withdrawing group at meta position. So what we are going to see here is, in chlorobenzene we already studied, in presence of sodium hydroxide, what we are going to get? We are going to get phenol. Sodium, the chlorine will be substituted by hydroxyl group, OH group, right? So now the next one, in chloronitrobenzene. So here we have taken chlorobenzene. Now we are going to take chloronitrobenzene. That means chlorine atom will be there as well as a nitro group will be there. So in the presence of nitro group, is there any change which is going to happen? We are going to see. Okay, as you can see, we have taken chloronitrobenzene here. In presence of sodium hydroxide, 443 Kelvin is only required. Here we have taken 623 Kelvin, higher temperature, right? So when nitro group is added, one nitro group is added, what happens? If the temperature has reduced to 443 Kelvin, and you will get, of course, there will be no change to the nitro group, only the halogen will be replaced by the hydroxyl group. So now we are going to take, as you can see, 1, 2, 3, 4, that is 2,4 dinitrochlorobenzene. So to this again we are going to add sodium hydroxide at 368 Kelvin. Again the temperature has reduced when there is 2 nitro groups. Again what happens? Hydroxyl group will substitute in place of chlorine and you are going to get the product. Okay. Now the last one, as you can see, it is 1, 2, 3, 4, 5, 6. That is 2,4,6 trinitrochlorobenzene is the one which is being formed. So in this case, we just have to warm it in presence of water. We just have to warm it. What is going to be formed? The halogen will be replaced by the hydroxyl group. So from here, what you can understand, without the presence of the nitro group, it was 623 Kelvin. In the presence of one nitro group, it became 443. In presence of 2 nitro group, it became 368. And in presence of 3 nitro group in the ortho as well as para position, when it is completely filled, we just have to warm it. We do not have to increase the temperature too high. It just has to be warmed. So it means that the presence of nitro group is making the nucleophilic substitution reaction easy, right? Now why is that happening? Because your nitro group is an electron withdrawing group. As discussed before, due to the resonance effect in haloarenes, what happens? The haloarene is electron rich. That is, in ortho and para positions, they will be electron rich. So to reduce the electron richness and make the haloarene more reactive towards nucleophilic substitution reaction, when groups like nitro groups, that is electron withdrawing groups, are taken, what will happen? It will take up the electrons from the benzene ring and reduce the electron richness of the benzene ring. Hence what happens? When the electron richness is becoming less, it will become more ready for the substitution nucleophilic reaction. So that is what is written here. The presence of electron withdrawing group at ortho and para position increases the reactivity of haloarenes towards nucleophilic reaction. Now why is that? Is just what I have discussed now, because it reduces the electron richness of the benzene ring and makes it more ready for the substitution nucleophilic reaction. However, there is no effect on reactivity by the presence of electron withdrawing group at meta position. So for example, if you are having a nitro group at meta position, this is ortho and this is the meta position and this is para position, right? So if you are having a nitro group at meta position, it doesn't make any change. It doesn't make any difference in the reactivity. But if you are adding more and more nitro groups to the ortho and para position, the reactivity increases. Okay. So in the next session, we are going to study about the electrophilic substitution reaction. So we have covered nucleophilic substitution reactions, electrophilic substitution reactions we'll cover in the next session, as well as some polyhalogen compounds we are going to study in the next session. So I hope the concepts that we have covered in this session is clear for you. So that's all for today. Thank you.